right. You, let's see, you are not in fact decorating it. Yes, you might have a little bit of, well, if I do this, you're totally not decorating it, so, all right. Yeah. You hate decorating videos. Yeah. I'm definitely in the school where every time I see my picture, I'm like, am I that ugly? I never like my pictures, you know, so. It's like, no, you look like you. I'm like, well, that's unfortunate. Okay, so anyway, let me get thing going here. All right, and fire away. What questions do you have? Hello, yes.
Can you explain the proton-proton chain and the standard cycle?
Yeah, so the proton-proton chain is one of the two ways that hydrogen can fuse into helium, the major pathways. CNO cycle is the other one. A low mass star like the sun, when it's on the main sequence, uses, well, actually, some low mass stars use the CNO cycle. Stars that are about 1.1 times the sun's mass and less use primarily the proton-proton chain. If you're more than about 1.1 solar masses, so just a little more massive than the sun, the hotter core turns out to mean that those use the CNO cycle instead. The net reaction is the same in both cases. So the proton-proton chain, remember I said that you can get some extra credit if you can duplicate this diagram. And you don't have to notice that the top and the bottom are identical to one another. So you get 3 points extra credit if you can duplicate this. It would be fine to draw this part and say, and then there's the same below. So proton-proton chain starts when two protons fuse. They form a deuterium. One of the protons turns into a neutron in so doing. So it's still hydrogen, but it's a proton and a neutron in the nucleus. That's heavy hydrogen. It's 2H instead of 1H because there's two particles in the nucleus, and that's called deuterium. Duo, you know, kind of two in other words. And when one of the protons turns into a neutron, it does that by spitting out a positron, an antimatter version of the electron, which quickly annihilates with an electron in the star nearby, and that produces a pair of gamma rays, and then a neutrino, which passes right out of the sun because neutrinos hardly interact with anything. Then another proton comes along, smacks into the deuterium. That makes helium-3. It's helium because it's two protons and a neutron plus a gamma ray. Meanwhile, then another helium-3 that got made the same way smacks into that helium-3, and two protons are spit out, so there's what is left over is a nucleus with two protons and two neutrons, because we start here with 1, 2, 3, 4 protons and the two helium-3s. Two of them get spit out though, and leave the scene, and then what you have left behind is the helium-4 nucleus, and so you get some extra credit. You don't have to if you like it. You get some extra credit if you can duplicate the full proton-proton chain. But the net reaction, which is what I want you to know for sure, is that notice that 1, 2, 3, 4, 5, 6 protons go in, but 2 protons fly back out again. So overall what happens is 4 protons come together to make a helium-4 nucleus. 2 of them turn into neutrons in the process. And because the helium-4 nucleus is about 0.7% less massive than the 4 protons that fused to make it, that missing mass, if you will, is turned into energy. The energy by which the star shines is the result of lots and lots of these nuclear reactions turning mass into energy by binding protons together into helium-4 nuclei. That's the proton-proton chain. I'm not even going to give you extra credit for this because spend your time doing other things than memorizing the whole CNO cycle here. Suffice it to say, it starts with a carbon-12 and 1, 2, 3, 4 nuclei fuse in a series of reactions that have as intermediate steps carbon isotopes, nitrogen isotopes, and oxygen isotopes. So that's why it's the CNO cycle, the carbon, nitrogen, oxygen cycle. And it's a cycle because in the last step, a nitrogen-15 nucleus is hit by a proton, and it splits apart into a helium-4 nucleus, and then you get back the carbon-12 that you started with. So it's a cycle because the carbon-12 is recycled, and it's free to participate in this process again. The net reaction is exactly the same, so 1, 2, 3, 4 protons fuse into a helium-4 nucleus. So the net reaction is the same in either case, and it turns out that the CNO cycle is favored at higher core temperatures, and the proton-proton chain at lower core temperatures. They're all blisteringly hot, but in other words, more massive stars than the sun that have hotter cores tend to use mostly the CNO cycle. And that's that in a nutshell. Before I move on to next questions, I always like to say any questions about what we just did. So any questions about this stuff? Yes?
I'm sorry, I'm sure you said it. What kind of star uses the proton-proton?
So proton-proton chain are main sequence stars that are less than about 1.1 solar masses, just a little bit more massive than the sun and below, including the sun, primarily use the proton-proton chain. The sun makes some of its energy, like 10% of its energy by the CNO cycle, but it's mostly the proton-proton chain. Above 1.1 solar masses, it flips to where the CNO cycle dominates, is more important. So, and then we didn't mention this, but as an aside, when you have hydrogen shell burning in later stages, that's always CNO cycle, because hydrogen shell burning is always at very high temperatures. So hydrogen shell burning always uses the CNO cycle. Another question about this? Yes?
So in the CNO cycle, doesn't it use carbon, nitrogen, and oxygen as catalysts and fusion?
So the overall the catalyst is the carbon-12, because that's the thing that gets recycled in the end. You could say that the other ones are catalysts too, in that they're ultimately not used up because nitrogen-13 keeps being generated by this process as well. But on the whole, the number one catalyst here is the carbon-12, because that's the thing that you both start and end with. So the carbon-12 is acting like a nuclear catalyst, something that participates in the reaction without being used up in the reaction. We use the same term in chemistry where you have a chemical that participates in the reaction from the beginning, but you also get it back in the end, so it doesn't get used up. So, any other questions about this? Yes?
Well, I guess so, yeah. Could you re-explain the, what's called the net reaction?
Yeah, by the net reaction, what I mean is the overall reaction. Overall. The overall reaction in both cases is that 4 protons fuse to form the helium-4 nucleus. There's 6 protons that go into the proton-proton chain, but 2 protons are spit back out at the end. So in other words, those kind of balance on the 2 sides of the equation. And the helium-4 nucleus that results has 2 protons and 2 neutrons in it, but those 2 neutrons used to be protons before they fused, but in that very first step, protons turn into neutrons. So in other words, the overall net reaction is that 4 ordinary hydrogens, 4 1H, or protons, a hydrogen with a single particle as a proton, becomes 1 helium-4 nucleus plus energy, because the mass of the helium-4 is less than the mass of the 4 protons that formed it, and E equals mc squared says that missing mass turns into energy. So you mind what I'm selling? Does that do it for you?
Yeah.
Okay. Any other questions about this, about the fusion stuff, the proton-proton chain CNO cycle? Yes?
How does 6 1H become the 1 helium plus energy?
There's no 4 there, so there's no 6 there. There's 4 protons fuse 1 helium-4 nucleus plus energy. That's what this is saying. 4 protons become 1 helium-4 nucleus plus energy. Helium-4 means there's 4 particles in the nucleus total, and it's divided into 2 protons and 2 neutrons. So in other words, this helium-4 at the end consists of 2 protons and 2 neutrons, but they all 4 used to be protons. So as a result, it's become a helium-4 nucleus, but 4 protons went into making it. And that's the net reaction because, yes, there are 6 protons overall that undergo fusions here, but you spit out 2 at the end. So when we talk about net, we're saying that of the 6 protons that participated, only 4 of them ultimately end up in the helium-4 nucleus, and 2 of them turned into neutrons as part of that. That's what it comes down to. Any other questions about this? Yes?
The energy part is just the 2 hydrogens that come off.
No. So they have some kinetic energy, so a little bit of it could be accounted there. But the energy overall is almost entirely in the form of these gamma rays that are produced here. That's where most of the energy is going, is in those gamma rays, as a matter of fact. Some of it also comes out as the neutrinos, but it's mostly in those gamma rays. And it comes from the missing mass. It's ultimately as a result of converting mass into energy. The mass of the helium-4 is less than the protons that went into it, and that missing mass is converted into energy, described by E equals mc squared, Einstein's famous formula. Any other questions about the fusion? Okay, you also had your hand up when I first asked for questions. So.
Can you talk more about neutrinos and the solar neutrino?
Sure, okay, so here's where the neutrinos are coming from. The proton-proton chain generates neutrinos every time in that first step. When 2 protons fuse together, they spit out a neutrino when one of the protons turns into a neutrino. And so the solar neutrino problem is this. Back in the 1960s, the technology was developed to detect neutrinos coming from the sun. The thing about neutrinos is that they only interact with other matter via what's called the weak nuclear force. The weak nuclear force. It's a very short-range force. It only acts on distance scales that are smaller than an atomic nucleus. And as a result, neutrinos hardly interact with anything. You can have light years of lead and send it, you can't really do it, but imagine you had a huge thing of lead that was light years long. A neutrino could go right through it without ever interacting with any of the lead in there. It's like it'd almost be transparent to the neutrinos. And what that means is that unlike the photons that are produced here, these gamma rays are quickly going to hit electrons and lose some energy and get redirected, and hit another electron and lose some energy and get redirected. The photons take something like 100,000 to 1,000,000 years for their energy to finally get to the surface after being created in the core, because they keep bumping around so much that it just takes them a really long time to get out. But the neutrinos stream right out. They pass through the material in the sun as if it weren't there. They hardly really even see that material in the sun. So when we detect neutrinos from the sun, we are detecting neutrinos that were made just 8 minutes ago, because it takes about 8 minutes for neutrinos, which are going the speed of light, to get from the sun's core where they're made to Earth. So detecting neutrinos allows us to probe conditions in the sun's core today, because we see them only a few minutes after they're made, because they travel near the speed of light. It doesn't take very long to get from the Earth to the sun at the speed of light. So neutrinos are very hard to detect because they hardly interact with anything, but they're not impossible to detect. And so it turns out that you can use one fluid that works is essentially a type of dry cleaning fluid. And so in the 1960s, essentially a huge tank of dry cleaning fluid was used to detect neutrinos coming from the sun. And the mystery was you could calculate the rate at which we should be detecting neutrinos coming from these nuclear reactions inside the sun, and we only saw about 1/3 of them, about 1/3 as many of them as we expected. So that's the neutrino problem, is why are we only seeing about 1/3 as many neutrinos from the sun as we expect? based on what we know, what we thought we knew about the physics of the nuclear reactions inside the sun. And one possibility would be we're wrong about that physics, we're wrong about the nuclear reactions. But another possibility, which turned out to be correct, is there are actually, it turns out, 3 types of neutrinos. There are what are called electron-type neutrinos, muon-type neutrinos, and tauon-type neutrinos, tau neutrinos. And the kind that are made in the sun by these nuclear reactions are electron-type neutrinos. But it turns out that neutrinos of one type, as they travel through space, will spontaneously turn into the other types of neutrinos. They oscillate back and forth from being one type of neutrino to another type of neutrino as they travel through space. And it turns out, and I can't explain this to you in a ready way, but it turns out that based on the very small masses of the different neutrinos, you would predict that if you had a bunch of electron neutrinos streaming from the sun to the Earth, about 2/3 of them would turn into other types of neutrinos by the time they get to Earth. And early detectors were only able to detect electron-type neutrinos. So the reason we were only seeing 1/3 as many neutrinos as we expected is because by the time the neutrinos got to Earth, only 1/3 of them were still electron neutrinos and could be detected. Now, that we know is the right solution because now we're able to detect all 3 types of neutrinos, and when we add up all 3 types of neutrinos, we get exactly what we expect. The total number of neutrinos coming from the sun is exactly what we expect. And so the resolution of the problem wasn't that we were wrong about the nuclear physics, it's that the neutrinos turn into other types of neutrinos on the way to Earth. And so that solved the problem. Question about that?
Yeah, so you said the solar neutrino problem, is that because the neutrinos turn into different neutrinos, that's the problem?
Yeah, well, that's not the problem per se. The problem initially was that we didn't know that neutrinos could turn into other types of neutrinos. We initially thought once an electron neutrino, always an electron neutrino. It turns out neutrinos didn't have any mass, that they were truly massless, which we originally thought. If they were truly massless, then they wouldn't turn into one another. And so you would expect that all the electron neutrinos coming from the sun would be detectable on Earth, and we didn't find that. We found only about 1/3 as many neutrinos coming from the sun as we expected. That's the problem. How come we don't see all the neutrinos from the sun that we're expecting? And the answer is because the little squirts were turning into other types of neutrinos on the way here just to trick us, so to speak. I mean, they didn't really want to trick us, but that's what they were doing. They were turning into other types of neutrinos that in the 1960s were not detectable, and so we weren't seeing them as a result of that. Now with new technology, we can detect them, and that got rid of the problem because now we're able to account for all of them. Okay, any more questions about the solar neutrino problem and how it is resolved? Okay, then let's have another question in general.
What is gravitational equilibrium and energy balance?
Yep, so gravitational equilibrium and energy balance, they apply in all stars. They are basic criteria that a star that isn't rapidly changing, that is pretty much staying the same from day to day like the sun, has to satisfy. Equilibrium means essentially balance or not changing over time. And so gravitational equilibrium refers to the fact that we've got 2 competing forces, if you will, working inside of a star. So the star's own gravity is trying to make it smaller because every part of the star is attracting every other part of the star. So if there was nothing counteracting that, the star would shrink because of its own gravity. But there is something counteracting that, namely pressure, which, because pressure is stronger deeper down and weaker higher up, pressure pushes outwards. And so gravitational equilibrium is the balance between the inward pull of gravity and the outward push of pressure. And so this figure here is illustrating the idea where the red arrows here represent pressure, and the green arrows represent the strength of gravity. And notice that or actually I should say the green arrows represent the weight of the layers above, the net weight pushing down from all the layers above each point. And notice that as you get deeper inside the star, there's more material above you, and so the weight pushing down gets bigger and bigger as you go inside the star. And the pressure in each layer pushing outwards has to be enough to balance that weight to keep the star from collapsing on itself or from expanding. If the downwards pull of gravity, the weight of all the layers above every level, is balanced by the upwards push of pressure, then everything will stay in place, so to speak. And so the green represents the weight getting higher and higher as you go in. The weight of the overlaying layers is getting higher and higher. The red arrows, notice they're longer in this towards the middle and shorter towards the top. That's indicating that the pressure is dropping as you go out towards the surface, because you don't need as much pressure out on near the surface when there's not as much weight above you that you need to support. That's gravitational equilibrium. It also works with pyramids of cheerleaders, stacks of acrobats. The idea is each of these, which doesn't show up well in the light, but each of these three guys, well, not the guy on top, but the guy on the bottom has to balance the weight of both the guys on top of him. The guy in the middle, he only needs to balance the weight of the one guy on top of him. So the guy on the bottom's got to be pushing harder than the guy in the middle does. Just like in the sun, the core has to be pushing up harder with pressure than the middle layers of the sun do, because it's got more weight to support. So that's the idea, is that in gravitational equilibrium, that balance holds everywhere. No matter where you are, the outward pressure balances the weight of the layers above you. That's gravitational equilibrium. Energy balance says that the rate at which the star is generating energy in its core is the same as the luminosity coming out of the star's surface. So the rate at which light energy is leaving the surface has to be the same as the rate at which energy is being generated in the core to be in equilibrium. Because if that wasn't true, let's say that the core was generating more energy than was coming out of the surface. In that case, energy would be building up inside the star because more energy was being created inside of it than was escaping from its surface. That could not be a stable situation, because you'd be building up more and more energy in the inside of the star, and that couldn't go on for very long. So if you're going to be nice and stable in equilibrium, you have to be losing energy from the surface at the same rate that you're generating it in the star's core via the nuclear reactions. And those two fundamental relations are necessary for any star to be stable. And so the star will naturally arrange itself so that that occurs, is what it comes down to. And so all main sequence stars are stable because they exhibit that kind of balance. Any follow-ups on that? Okay, so somebody asked me another question. Okay, you've already asked one, so I'm going to go to the back here, and I'll get you. It's not that I don't want you to ask any more questions, not one per customer, but yeah, definitely.
What are the sunspot and magnetic cycles?
Yeah, so sunspots and magnetic cycles. So, yeah, we didn't talk about this in class, even though it's my topic. That's my what I study professionally, but there's only so much time. So, sunspots are apparently dark areas on the surface, in the photosphere, the quote-unquote surface of the sun. So here's a white light photograph of the sun, and you can see sunspots on it. Here's a zoom in of that. Here's the size of the Earth to scale. And yeah, did we talk about this in class? I don't think we did. We did? Yeah, we didn't. Okay, so here's the Earth shown to the same scale to emphasize sun big. So sunspots don't look that big, but they're big. I mean, this sunspot group here is much larger than Earth is. And they look dark because they are cooler than the surrounding photosphere, the surrounding surface layers of the sun. And we know from the Stefan Boltzmann law that hotter means brighter. So the surrounding photosphere is at about 5,800 Kelvin. The spot umbras, the central part of the spot, the darkest part of the spot, is more like 4,300 Kelvin. And so as a result, it's not emitting as much light. It's not that it's actually black. It looks black in the photograph, but it's really that it's just not nearly as bright as the surrounding surface is. And so as a result, if you set your camera exposure to show the surrounding surface nicely, you underexpose the spot and it looks dark in comparison. And it really is dark in comparison. They actually emit a lot of light, but just not nearly as much light as the surrounding area does. Yes?
Did you say that the sunspots are hotter than?
They're cooler. The sunspots are cooler than the surrounding surfaces, and that's why they are darker. Because remember that hotter means brighter, cooler means darker when it comes to giving off thermal radiation. And so they look dark simply because they are cooler than their surroundings. They're still giving off a lot of light, but the surrounding photosphere is giving off even more light. And there are spots on other stars that are way bigger than sunspots are on the sun. So for example, this is the poetically named star HD 12545. It brings tears to my eyes to think of the beauty of that name. It's a subgiant star, and it's got a star spot on it. Sunspots on other stars are called star spots, and that star spot on HD 12545 is actually bigger than the entire sun, and it's bigger compared to HD 12545 than sunspots are compared to the sun. My research specialty is to study star spots on other stars. That's what I do for my research. I involve students with that, in that a rotating star with spots on it, the dark spots make the star dimmer when the spots are visible to us. And so if you monitor a star's brightness over time, which we do at Perkins Observatory, we can see that the star's brightness goes up and down because of the spots on it. And then I developed a computer program that's able to take those variations and map the star spots, make a rough map of the star spots on the star. And then I collaborate, for example, with a OWU student who graduated back in 2008. She and I still collaborate studying star spots using, for example, the Kepler mission, which looks for exoplanets passing in front of stars. But exoplanets passing in front of stars, to detect them, you need to be able to see the star get dimmer because of the planet in front of it, which means it detected a lot of star spots by accident too. So she and I published papers about star spots from the Kepler mission data, for example, and we want to do that with the so-called TESS mission now. But anyway, enough about me. Sunspots are cooler because they have magnetic fields in them, and it turns out that the strong magnetic fields inside of sunspots suppress convection. They suppress the up and down motion of gas in the sun's outer layers, in the so-called convective zone of the sun, which is the outer portion of the sun if you take a kind of cross-section through it. So if I go back here, this is the sun's convection zone in the outer layer where energy is transported by hot gas rising and cooler gas sinking. Sunspots suppress convection, which means not as much energy is coming up into them from below compared to other regions, and that's why they cool down and become darker. And so that's kind of the big picture, is sunspots are regions of strong magnetic field on the sun, which chokes off convection, and therefore they cool down because not as much energy is flowing into them from outside. And then I mentioned on the sheet about the solar magnetic cycle versus the sunspot cycle. And the deal with that is that if you make a plot of the number of sunspots on the sun versus time, we find that it looks like this. The number of sunspots is going up and down and up and down and up and down. Notice this is 1900, this is the year 2010, so this is this is like 110 years of observations. And so the number of sunspots goes down and up, and down and up, and down and up. And the time from one maximum number of spots to the next is about 11 years on average. So there's an 11-year sunspot cycle. There's an 11-year cycle in the number of spots on the sun. But there's a 22-year magnetic cycle, because it turns out that, for example, sunspots often come in pairs, and what happens is that the magnetism of the two pairs of the paired sunspots is opposite. So if one spot corresponds to the field line sticking out of the sun's surface, which would make it a north magnetic pole, then the other spot paired up with it has the field line sticking into the surface, which would make it a south magnetic pole. And if we see that that's the order in the sun's northern hemisphere, that the ones on the right, out in front of the direction of the sun's rotation, so the sun is spinning like the Earth is, it takes a whole month instead of the Earth, which spins in a day. The sun is spinning just like the Earth is from west to east. That means that on this picture where the sun's north pole, north geographic pole is up, then notice in the northern hemisphere, south magnetic polarity spots are out in front in the direction of rotation, north ones are in the back, and it's the opposite if you cross the equator. In the other hemisphere, north is in front and south is in back. And the thing is that when you go from one sunspot cycle to the next, I'm trying to see if I've got another picture of that. Yeah, I don't, unfortunately. When you go from one to the next, that flips around. The sun's overall magnetic field flips from one sunspot cycle to the next. So if this is one sunspot cycle, then when we get 11 years later to the next sunspot cycle, the N's and S's would reverse. The direction of the magnetic field on the sun, the overall magnetic field reverses. And so the sun has an 11-year sunspot cycle, but a 22-year magnetic cycle, because you have to go through two sunspot cycles to get back to the original configuration of the magnetic field. So for example, it's kind of like this. Here's this remote, okay? Here's the top side of it with the buttons, here's the bottom side of it with not the buttons, okay? So now, I put it on the table, the buttons are up. I flip the polarity, I flip it around, analogous to flipping the direction of the magnetic field. So now it's the other way around. Now the buttons are down, okay? Think of that like the sun's magnetic field. So here it is. 11 years later, the field has flipped. 11 years later, the field flips again. Am I back to the original configuration after I flip the flip? I am. So in other words, in 11 years, the magnetic field flips around, and then 11 years later again, it flips again, and so you're back to the same magnetic configuration. So there's an 11-year cycle in the number of spots, but a 22-year cycle, 2 sunspot cycles to get back to this overall same magnetic field pattern. And so we say there's an 11-year sunspot cycle, but a 22-year magnetic cycle is the idea there. Any further questions about that topic? Yes?
Why does the magnetic field reverse every 11 years?
That's complicated. Let's talk about that later, but I'm not going to ask a question about why it reverses on the exam. So for efficiency, we'll just take it as a granted that it does. That's a very, very interesting and complex question, and it still hasn't been completely solved, which means there are some people who get to have a job trying to figure it out, and it's complicated. But there is some understanding of that, which I'll be happy to talk with you about later. Yes?
Like what happens in the core that serves as the definition of the construction?
Of the what?
Of the core of the sun?
Oh, so the core is where it's hot enough for nuclear fusion in the sun to be happening. Right, that's what, so in other words, we divide the sun into 3 layers, and for that matter, other stars also. There's the core, there's the radiative zone, there's the convective zone. And the core is where nuclear reactions are happening. It's where it's hot enough for nuclear reactions to be taking place. Outside that is the radiative zone, where energy is being transported by radiation from the core towards the surface, by the fact that it's hotter towards the core and cooler towards the surface, so more energy is flowing out than flowing in as a result of that. So there's a net transport towards the surface. And then in the convective zone, it's the rising of hotter gas and the sinking of cooler gas that is transporting energy from the hotter interior up to the cooler surface. And so that's how it works for the sun. For more massive stars, as we mentioned recently, that structure flips around in that if you get a bit more massive than the sun, and it turns out it agrees essentially with the CNO cycle versus the proton-proton chain, stars which are more massive than the sun on the main sequence and have the CNO cycle happening in their cores to generate energy from hydrogen fusion, their cores are convective, and outside the core all the way to the surface is radiative. So lower mass main sequence stars, well, the lowest mass main sequence stars are convective throughout, and then from about 0.3 solar masses to a little more than 1 solar mass, they are radiative on the inside and convective on the outside, and then you go above that and that flips around. They're convective on the inside in the core and radiative on the outside. So it's just a fact that they flip around. In both cases, the significance is that what's in the core stays in the core, that you're not mixing stuff from outside the core down into the core, which is why stars, unless, except for the lowest mass stars, they waste most of their fuel. They never fuse it because most of the hydrogen stays outside the core. It never gets the opportunity to be fused. So most stars are not, many stars are not very efficient in the way they use their fuel. They never use most of it because it stays outside the core. Does that do it for you? Okay, all right. Next question. Yes?
Could you explain the electron degeneracy pressure and why that's not affected by temperature?
Yeah, so I will do that briefly. I'm not going to ask on the exam why it's not affected by temperature, but I will, and not that I don't think it's important, but and again, electron degeneracy is hard to fully explain without quantum mechanics, like full blown. But the basic idea is this, that we know that in an atom, there's only certain allowed energy levels. And if you've taken chemistry, then you know that each orbital can only fit 2 electrons, and they have to be having opposite spins. That's called the Pauli exclusion principle. It's the reason for the periodic table. It's the reason why all the electrons in an atom don't just sit down in the ground state, in the 1s orbital. Only 2 can be in the 1s orbital. And then you can fit 2 more in the 2s orbital, and 6 more in the 2p orbitals. And then there's 3s and 3p and 3p orbitals and so forth. The Pauli exclusion principle, the rule that only 2 electrons can be in any given orbital, is why electrons in atoms are forced to occupy higher and higher shells, higher and higher orbitals, instead of all having the lowest possible energy being down in the ground state. And so if you have a multi-electron atom, most of the electrons have a lot more energy than they would if they could be down in the lowest energy level, the ground state. That actually applies even if you're not talking about atoms. Even in this room, strictly speaking, really there are orbitals that the atoms are able to occupy. And in a gas of electrons in the core of the star, the electrons are only allowed to have certain energies. Now the orbitals, the quantum wave functions, are spread over the entire volume of the core,